Hello everyone and welcome to today's episode on this web channel. In today's lesson, we shall be looking at the Quasilinear PDE, how we can use the method of characteristics equation to solve a Quasilinear PDE. Remember, we are still on the same topic, solution to first order partial differential equation using the method of characteristics equation. If this is your first time and you haven't subscribed to the channel, kindly hit on the subscribe button for me. So without wasting my time, let's set the ball rolling. So in our previous lesson, we talked about quasi-linear, and we said that for a PDE to be a quasi-linear, then it should be of this very form. So you can see that when we expand the bracket, we are going to have the dependent variable multiplying its derivative. So we are talking about this. We are going to have u multiplying its derivative. And this makes the PDE a quasi-linear. So when we expand the bracket as well, in this term, we are going to have the dependent variable u or the unknown function u multiplying its partial derivative with respect to u. And this makes the PDE quasi-linear. So when you look at the question that we are going to solve today, you can see that we have the dependent variable u multiplying its partial derivative with respect to x. The same thing applies to this u multiplying its partial derivative with respect to y. So this makes the PDE a quasi-linear PDE. So in solving a question on quasi-linear PDE using the method of characteristics, we are going to apply the same steps, the same method, the same approach that we use when we are looking at the semi-linear PDEs and then the linear PDEs as well. We are first going to identify our A, our B, and our F from the equation given. So let's do just that. So from the equation, our A is the coefficient of ux, that is this one. So we have our A is equal to x y squared plus u, and then our B is the coefficient of what? Uy, that is minus y s squared plus u, and then our F is the term on the right hand side of the equal sign. So we have s squared minus what? Y squared multiplying u. So once we have this, we form the characteristics equation. And we know that the characteristics equation is giving us dx all over a is equal to what? Dy all over b. And this is also equal to what? Du all over what? The function f. So once we have this, we are just going to plug in this. So we are going to have dx all over this. And then we have dy all over that. And then we have our du all over this. So you can see that the method of characteristics has converted or has reduced the PDE into an ordinary differential equation form. And in that case, we can make use of any method that we know for solving ordinary differential equation to solve this. And we can also use our simple integrating technique. Very, very easy and then simple. So in our previous lesson, we also said that when f is not equal to 0, that means we are going to get two solutions from the characteristics equation. So you can see that here our f is not equal to 0. So we are going to form two equations, and that is going to give us two solutions for this partial differential equation. Once we get that, we make them into a single solution. So it means we are going to form two solutions. Very, very easy and then simple. Get that in mind. So from here, we observe that we have the x over x, the y over y, and then the u over u. And this means that we can separate the variables and then integrate. But we have a lot of chaps here. So we have these chaps. All these chaps makes it difficult for us to integrate directly. So what we are going to do is to clear these chaps away. We are going to clear it. And we can't just clear it. We can do that by applying our algebraic approach or algebraic methods. We can see that questions on quasi-linear involves a lot. In fact, involves a lot, and it demands a lot of algebraic manipulations in order for you to maneuver your way out. So if you are algebraically good, in fact, you will find your way out. So what we are going to do here is that from here we can see that the x all over this, we can write it as 1 all over x dx all over y squared plus u, y squared plus what? U. We can write this as that because we know that 1 over x dx is the same as what? Dx all over what? X. And this is what? Divided by that. So we can write it as divided by y squared plus u. Now we know that with this, we can write it as dx all over x times what? 1 all over y squared plus u. So when we multiply, we are going to get dx all over x multiplying that y squared plus u. So it means that we can write it as that. It is simply applying your basic algebra when you have, let's say, 1 all over, let's say, 2 multiplying 4. So we can write this as 1 over 2 all over 4. Because with this, we can write it as what? 1 over 2 divided by what? 4. And we can write it as 1 over 2 times 1 over 4. So when we multiply, we are going to get 1 all over 2 multiplying 4, which is the same as what? That. So it means that when we have this, we are going to write it in this way form. Very, very good and then interesting. So we have 1 over what? X dx all over what? Y squared plus u. And then we have equal to, we are going to apply the same concept here. We are going to write it as 1 all over y dy all over minus x squared plus u. And then with this one as well, we are going to apply the same concept. We have u, 1 over u, 1 over u du all over x squared minus what? Y squared. Very, very interesting. Now from here, what we are going to do is we are going to apply some basic knowledge that we had in SHS and then GHS level. So with that, we said that when we have two fractions, let's say 3 over 6, and then this fraction is equal to 1 over 2. When we have two fractions and then they are equal like this, we can add their numerators or we can subtract their numerators and then the denominators as well. So we can write this as 3 plus 1 all over 6 plus 2, and this is equal to any of the fractions, so 3 over 6, and this is also equal to what? 1 over 2. Let's check it out. So when we add them, we are going to have 4 all over what? 8 is equal to 3 all over 6 is equal to 1 all over 2. Now when we break them down, we are going to have 1 over 2, 1 over 2, 1 over 2. So if we have to subtract it, we are going to get the same thing. So this means that when we have a fraction of this well form, we can add them and then equate it to the third fraction or equate it to any of the fractions. But we are going to apply the same concept here. Now since these are three fractions and then they are equal, we can add this to that and then equate it to the third fraction. That is what we are going to do here. We are going to apply the same principle here. So we are going to have 1 all over x dx plus 1 over y dy all over this plus that. So we have y squared plus u minus x squared plus u. This one is plus, but because of the minus, it has taken over. So we are going to have 1 over u du all over what? S squared minus y squared. Very, very interesting. Very, very interesting. So as I said, with Quasilinear, your algebra should be very, very strong. So let's continue from here. So from here, we have 1 all over x dx plus 1 all over y dy all over. Now when we expand this bracket, we are going to have y squared plus u. Let's remove the bracket. So we have minus. This will give us minus s squared minus what? U. And this is equal to 1 over u du all over s squared minus what? Y squared. So from here, we can see that one of the u will cancel themselves. So this u cancel this u. So we are left with what? We are left with 1 over x dx plus 1 over y dy all over what? Y squared minus what? S squared. And this is equal to 1 over u du all over s squared. So you can see that we are having this, the denominator seems to be the same, but we have here to be positive y squared and here to be what? Negative y squared. If we are to make the denominators the same, we can equate their numerators, because in our basic knowledge in algebra, when you have 1 over 4 and then let's say x all over 4, since the denominators are the same, we can what? Equate their numerators to have 1 is equal to x. And once we have this, we can what? Integrate them directly. And that is what we want to do here. So we are going to make the denominators to be the same. So we have 1 all over x dx plus 1 all over y dy all over y squared minus what? S squared. Now let's make this one to look like this. And we can do that by multiplying the top and down by negative 1. So we multiply here by negative 1 and then multiply here by negative 1. Now when we do that, we are going to have the top to be negative 1 over u du, and then we are going to have, this will give us minus s squared and this will give us positive y squared. So let's write it as y squared minus what? S squared. Now you can see that the denominators are the same, and once the denominators are the same, we can equate their numerators. So we have 1 over x dx can be written as dx all over x, and then we have plus dy all over y is equal to minus du all over what? U. Very, very interesting. Now once we have this, we can just integrate. Everything has become very, very simple, so we can integrate them term-wise. So let's integrate this, we integrate this, and then we integrate this. So we are going to have our ln x, and then when we integrate dy over y, we are getting 1 ln y is equal, when we integrate the u over u, we are getting ln what? Ln u. Since all of them are ln, let's take the constant of integration to also what? Ln. Since we will be looking at 2 equations, we are going to call this one C1. Now once we have this, we are going to write this as ln, applying our basic knowledge in logarithm. Since we have ln and ln, they are adding, we can what? Multiply their arguments, so we have x multiplying y. And then we can also write this as the ln. Since we have lns, they are adding and then subtracting, we can what? Divide the arguments, so we are going to have C1 all over what? U. Now we are interested in making C1 what? The subject. So let's take the e on either side of the equal sign, so that the e will cancel the lengths. So we have e cancel the length, the e cancel what? The length. So at the end, we are having xy is equal to what? C1 all over what? U. We want to make C1 the subject, so let's multiply through by u. So we are going to have x y u is equal to what? C1, when we multiply through by what? U. so that this will cancel this. So we have that. So this is one of our solutions. So this is one of our solutions. So we have our first solution. Very, very easy and then simple. So as I said, questions on quasi-linear involves a lot. So we are now going to look at the second solution. Since we are having our f not being equal to 0, we are going to form the second equation. From that, we are going to form what? The second equation. Form the characteristic equation here. So let's write the characteristic equation. We have dx all over x So with the second equation, we should have paired the u with any one of them. But realize that we are having a lot of variables in x, y, and u. So if you pair the u with that, it will be very difficult for us to integrate. And then we pair this with that, it will be very difficult for us to solve. So we are going to apply another approach, another algebraic approach for us to get our second solution. Now what we are going to do here is we are going to multiply this term by 1. You multiply this by a factor of 1. How can we multiply a factor of 1 for these two terms or for these two fractions? Now you know that when we multiply here by x over x, you know that this s will cancel this s, we have 1. So it means we can multiply this by x over x, and then we multiply here by y over y. Y over y is the same as 1. So we've multiplied by what? A factor of 1. So we have x dx all over x multiplying x y squared plus u, and then we also multiply here by y over y, so we have y dy. This will give us what? Y squared, and then we have s squared plus u, and this is equal to what? Du all over s squared minus y squared multiplying what? U. So s plus s will give us s times s will give us what? S squared. So let's write it as that. S squared. Very, very interesting and then simple. Now once we have this, we are going to apply the idea that we used when we were looking at this particular part here. We are going to apply the same concept when you have two fractions and then they are equal 3 over 6, and then let's say 3 over 6 and then 1 over 2. We are going to add them to get what? 3 plus 1 all over 6 plus 2. So we are going to apply the same concept here. So we have x dx plus what? Y dy, x dx plus y dy all over what? S squared y squared plus u, and then we have, since plus will be overshadowed by the minus, we have minus y squared, then we have s squared plus u, and this is equal to the third fraction, which is what? Du all over s squared minus y squared u. Now from here, what we are going to do is we are going to expand the denominators, okay, to see if we will have the denominators to be the same so that we can equate their numerators. So let's expand the denominators. Dx plus y dy all over, this is going to give us s squared y squared plus s squared u. This is giving us minus s squared y squared, and then we have minus y squared and then u, and this is equal to what? Du all over u multiplying s squared minus y squared. So from here we can see that some of them will cancel. You can see that positive s squared y squared will cancel negative s squared y squared. So we are left with s squared u minus what? Y squared u. Very, very interesting and then simple. Let's continue. So you have our x dx plus our y dy all over, where is it, s squared. Let's factor u out. So we have u s squared minus what, y squared. And this is equal to u all over what, all over u s squared minus what, y squared. So from here, you can see that the denominators are the same, and once they are the same, we can just equate their numerators. So let's continue from here. Very, very lengthy question like that. So when we equate their numerators, we are going to have x dx, x dx plus y dy is equal to what, du. So from here, we can integrate them term-wise. We are going to integrate this, and then we integrate that. So when we integrate x dx, we are going to get what, s squared all over 2. And then when we integrate this, we are going to get what, y squared all over 2. And then we add the constants of integration. Okay, let's add it to the right hand side. When we integrate the u, we are going to get what, u plus the constant of integration. Since we had our first constant to be c1, let's make it what, c2. We want to make c2 the subject. So what do? Let's bring u to the left hand side. So we have s squared plus y squared all over 2 minus what, u is equal to c2. Let's eliminate the denominators. Let's remove the fraction by multiplying through by what, 2. So we are going to have s squared plus y squared minus 2u is equal to what, 2c2. A constant times a constant will still give us a constant. So we are going to write just c2. So we have c2. Very, very interesting. So we are done with our second solution. So this is our second solution. This is our second solution. So we have our first solution to be c1, which is this. And then we have our second solution, which is this. And whenever we have two solutions, we always put them together, or we made them together to give us one solution. So it is either one becomes a function of the other. It is either c1 becomes a function of c2, or c2 becomes what, a function of c1. So let's make c1 to become a function of what, c2. You can also make it c2 to be a function of c1. It doesn't change anything. So our c1, we had x, y, u is equal to a function of c2. So this is c2. We are going to have a function of s squared plus y squared minus 2u. So this becomes our general solution. This is what, our general solution. Very, very interesting. So we have our general solution. This is our general solution. But I realized that in the question we were given an auxiliary condition or initial condition. So we have to find the particular solution. So we have to continue and then we find our particular solution. We are continuing from this side. So we have our general solution to be in this well form, right? And then we have the auxiliary condition. So let's write our general solution. We have x, y, u is equal to a function of s squared plus y squared minus 2u. Now we have this auxiliary condition x, ux, 3x is equal to s squared. Now this means that wherever we see x in the general solution, we should plug in what, x. And wherever we see y in the general solution, we should plug in what, 3x. And wherever we see u in the general solution, we should plug in what, s squared. Very, very interesting. So we are just going to plug in this in the general solution. So we are going to have our x is still x, so we have x, multiply our y is what, 3x, so we have 3x, multiply our u is what? S squared. So we have S squared, and this is equal to a function of what? Our S is still x, so we have S squared. Our Y is what? 3x, so we have 3x all squared minus 2. Our U is what? S squared, so we have 2S squared. So when we multiply them, we are getting what? 3x raised to the power 4, right? And then we have a function of, this is giving us S squared, plus this is giving us what? 9x squared, and then we have what? 2x squared. So we have our 3x squared is equal to a function of, when we do the algebra, we are going to get this giving us 7 and then 8. So we have 8x raised to the power 2. So at this very point, this is 4, sorry. So what we are going to do here is that we are going to let any variable at all to represent what is in the function. So we are letting p to represent what is in the function 8x squared. Now from here, let's make x squared the subject since we have x raised to the power 4. Okay, so we have our x squared is equal to what? P all over 8. We can decide to use this, or we can even take the square root on either side of the equal sign, so that this will cancel. Then we have our x to be equal to what? Root of what? P all over 8. So this means that wherever we see 8x squared, we are going to plug in what? P at this very place. Wherever we see 8x squared in this equation, we are going to plug in P. And wherever we see x, we are going to plug in P over what? 8. Root of P over 8. Very, very interesting. So we have here to be what? 3x raised to the power 4. So we have 3 is the constant, so let's write it. We have our x to be what? Root of P all over what? 8. So we are having root of what? P all over 8, and all of this is raised to the power of 4. And then we have f of p is equal to 8s squared. So sorry. We have our 8s squared is equal to p, so we have p. Now with this, we can write it as 3 p all over 8 raised to the power 2, because the root sign will cancel one of the square. Good. And then you have our f of what? P. So at this point, what we are going to do is we are going to go back to the general solution, and then we pick what is in the function of the general solution to replace what? P. We are going to pick what is in the function of the general solution to replace what? P. So we are going to have f of, we said our P, we are picking what is in the function. So we have s squared plus y squared minus 2u is equal to, we have 3, and then bracket. We are saying that P is what? This. So we have s squared plus y squared minus 2u all over what? 8. And this is all raised to the power of what? 2. So we have power 2. Now with this, we can write it as 3, and then we have s squared plus y squared minus 2u all raised to the power 2, and all of it is over what? 64, because 8 times 8 will give us what? 64. Therefore, the particular solution to this Quasilinear PDE is what? U at x comma y is equal to that. So this becomes our particular solution. Very, very easy and then simple. So this is our particular solution. Very, very interesting question. This brings us to the end of today's lesson. See you tomorrow. Bye bye.